Okay, let's move on, and now I will consider this topic of our day 4. It's glass form amenability and aging mechanism. This is a very important topic in the field of phase change memory, because both this glass formability and aging mechanism, they are connected. And these properties of like aging mechanism or aging of the amorphous phase change materials, it's an unwanted process because it influences the multi-level capability of our cell. We had a lecture yesterday on brain-inspired computer. There we need different levels, at least 3 bit or more, and if you have such a resistant drift in our cell, so what is the resistant drift? This is the change of resistance of amorphous state over the time. Here this shows you the graph from the first lecture, and this is low resistance state. The resistance does not change over the time, and here the resistance drift is changing, and what we can see it's going up. So here you see the resistance increases, and if we make conductivity measurement, the conductivity decreases. And we see here the relaxation of the amorphous state, but not towards the crystalline state. Otherwise, we would see the change of the resistance in this direction. And so, if we have such a resistant drift, and to get multi-bit cells, we need different states, at least 8 states. And if the different states, the resistance will change, then at some points the resistance will be overlapped, and so we cannot reliable to read the information from the cells. The drift resistance is defined by this equation. So this is logarithmic R divided by R0 divided then T by T0. They are R and R0. This is the resistance at time T and T0 respectively. So let us look to the basic properties of the amorphous structure of our phase change material. And first, please, I would like to define make again some definition what glass is. So in the 1932, Zacharias he stated some rules for the definition of glasses based on observation of oxides, and he stated that no oxygen atoms may be linked to more than 2 cations. The cation coordination number is small, 3 or 4. For amorphous GST it's a little bit different. Oxygen polyhedral shares corners, not edges or faces, and for 3D networks at least 3 corners must be shared. But this Zacharias rule, it does not consider all the modified, do not consider at all modified oxides or multi-component system, or even non-oxide glasses. So we need a new definition of glasses. I will make it on the next slide. Now let us look how to obtain the amorphous state of solids. Here we can use physical vapor deposition, mechanical gradient or irradiation, or by melt quenching processes. And this is how we make the amorphous state in the phase change memory device. So now again, let's us back to the definition of the glass. So the glass, this is a non-equilibrium, non-crystalline condensed state of matter that exhibit Tg. Tg, this is the glass transition temperature. If you look to the graph of enthalpy over the temperature, and if our material transforms to the glass, it will always get like a TG, glass transformation temperature. So if we start from the liquid state, then we go to the transformation to the super liquid state, and then at some point at TG, our materials goes to the glassy state. So from this both states, like a super cooled liquid, we can go to crystalline state if we can cool down our system very fast, and also from the glassy state can be also, this process can be also done. The TG is also this glass temperature. This is divided as a temperature corresponding to the equilibrium viscosity of 10 to the 12 Pascal. So you can also see, also like define that the viscosity of these three both stages, they also different. Like liquid has the high mobility here of atoms and here, so they have like low viscosity, and this is the high viscosity and glassy state. It has a higher viscosity, so the mobility of atoms in the glassy state not so high as this in this super cooled structure. So the viscosity, this is the viscosity and atomic mobility, as I said, they are linked. And the viscosity, this is a measure of fluid's resistance to flow, and is directly affected by the assay with which atoms can move or rearrange themselves. So in this state, as I said, the viscosity increases, and here in this state decreases. And so this viscosity, this is the measure of glass forming fluid to flow, and at T larger than TG, this glass forming liquids have low viscosity, and upon cooling this increases, and by order of magnitude. Based on this viscosity, the angels, he classified the glass, the materials into classes. Like if the material possesses this viscosity on temperature linear, then we can say this is the strong liquid. So it follows the Arrhenius equation, and if it shows this like bold T variation, or then this is the fragile liquid or wet glass former. So now let us look to the glass forming ability. So what is it, and what is the measure of glass forming ability? So glass forming ability is the tendency of material to form a glass then quenched. And the measure of this glass forming ability 1, this is also was introduced by Angel. Here this is the fragility index, so which can be obtained by the slope of the Angel curve. And here this M was introduced to characterize the flow of atomic mobility with temperature above TG, and this is defined as like by this equation. So this is fragility index. And strong liquids, they have low M, this index, and they should have greater glass forming ability than fragile liquids with high M values. So also this higher M values corresponds to a more rapid decrease in viscosity upon heating above TG. And this M is related to atomic mobility and plays an important role in crystallization kinetics and the switching behavior of PCM. So there is also another criteria of glass forming ability. It was introduced by Senkov, so-called Senkov parameter. and this defines by this equation. This is the empirical parameter. This combine the glass forming temperature, and he found that if his parameter larger than 0.65, this is the strong liquid, and if this parameter is less than 0.65, this is fragile liquid. Here we can also find the dependence of the parameter, set of parameter on the temperature, here cooling rates, and we can see here that this is the open diamonds. This is metallic glass former, and this is also it's non-metallic, and this metallic glass former. And so we can see that these are strong glass former, and this is bad glass former. This is the 0.65 somewhere here. So by this we can also identify the glass forming ability. So now let us look to the experimental data obtained on phase change materials regarding glass forming ability. So first, this is the viscosity on temperature, and for different materials like GAT and GST and AST, we can see this type of the spot, and this is the first signature that this material the glass forming ability is not good. So it's fragile liquid. Then if you look to the some parameters for phase change materials, again for GST225, germanium telluride, like antimony telluride, AST. So if you look to the M parameter, this is high for GST and GET, DT, and also this Senkov parameter is also low, more than 0.65. It shows also the fragile liquid. If we compare it with, for example, non-phase change materials, we can see that this to these non-phase change materials, let's look to the typical selenium-based chalcogenides. Then what we can see here, that we can see that the M parameter is very low. It's on the range between 18 and 27. Also the Senkov parameter is very large. So this is the signature of strong glass formers. And in the case of phase change materials, we can see from all this data that these are bad glass former. So the glass forming ability is very poor. And here also to achieve this amorphous state, we need cooling rates in the range of 10 to the 9, 10 to the 11 Kelvin per second. Here I would like to say that glass formers have stark tendency to crystallization more. We would use generally to relaxation of structure. So now relaxation of glazes. So any glazes does not matter. It's phase change materials, amorphous phase change materials, or other glazes. They tend to relax their structure toward low energy states, and this relaxation it accompanies with different changes like its structure and physical properties, like entropy, density, diffusion, and electrical resistivity. We can consider there are two types of relaxation of glasses. This is one first type. This is alpha type. This type of relaxation is frozen below TG. And what we are interested, this is the beta relaxation, and this is an important process in the glassy state. Why it's important? Because the beta relaxation describes local fast atomic motions involving a group of atoms confined by low mobility matrix and promotes accelerated aging and rapid crystallization in metallic glasses. So this is the common definition of beta relaxation. How to measure this, how to study this beta relaxation? So we can use dynamical mechanical analysis, DNA, or powder mechanical spectroscopy. So let us look to the results on powder mechanical spectroscopy. Here you study like powder mechanical spectroscopy. This is a technique used to study the relaxation behavior of materials. Particularly we can study phase change materials or non-phase change materials. You study this loss of model E here, how it behaves. And if you look to the two types of material, one are non-phase change material and one are phase change material. And if you look to the temperature, like here the TG, then you see a nice peak here without any features close here to this point. However, in the case of phase change materials, GST225 or AST, we see here some interesting feature, like the formation of excess wings, like here, and this is the sign of so-called beta relaxation in phase change materials. In the non-phase change materials, we don't find these wings, excess wings, so they do not show this beta relaxation. And so if you want to reduce resistant drift of your phase change material, you have to restrain somehow atomic motion and suppress structural relaxation. As again, I would like to mention that it's structural relaxation, in which direction from the resistance measurements, I would say it's more into the direction to the supercooled liquid, because the resistance increases instead of decreasing. So now how to overcome or reduce resistant drift of the materials. One is, this is from the first lecture, one is you can use optimize your device, and this is so-called projected phase change memory device. Here I would like to explain you a little bit more about this projection device. So you have our phase change material, and you introduce an additional element, so-called projection segment. And this is the segment, this is high conductive segment, maybe metallic layer. And then during amorphization, you induce amorphization in your cell. So you have two parts, amorphous and crystalline part. And then this is the bottom electrode, and you want to measure the resistance of this state. So you allow the current to flow here, and then current flow here. But if it meets the amorphous phase, it does not go through it. So instead it goes like make another path. This would be the read path. So it goes here from the metallic layer to the top electrode. So by using this, you can reach really low values of resistance drift. It was introduced by IBM, 2023. You can also optimize your material Here, this is on the side of materials engineering. One, you can produce the superlattices consisting of germanium telluride, antimony telluride, or you can combine different other materials. And by this you can reduce the resistant drift alone. This is the resistant drift of amorphous GST. This is this new value. It can be very dependent on the maybe sputtering technique and materials itself, but it's on the value 0.025, 0.026. It's measured 0.025 in this work. In our work we measured also this resistant drift of pure GST. This was a little bit larger. But if you make a superlattice of GET and SBT, you can reduce this resistant drift after a very low value of 0.0.6 here. And this is very close to the crystalline germanium telluride, antimony telluride layer. So this reduces a lot the resistant drift. What you can also do, you can also try to optimize the structure of your GST material by alloying or maybe by doping. This is also very famous method. Like we know, you can use iron implantation. In this case, we used alloy with selenium. And here this is the antimony selenium. This is a little bit different composition, not GST based, but antimony selenium based. And here, if you adjust the composition, we can get also very low value of resistance drift on the order of the superlattice structure. So. Now let me conclude this part of my lecture. So we study about glass forming ability, and this is tendency for material to form a glass state when quenched. Glass forming ability is connected to the atomic mobility and plays an important role in crystallization kinetic of PCMs. The fragility index and set-off parameter. This is the measure of GFA, glass forming ability. These angels here introduce the classification of glasses on strong and fragile. And here by fragility index you can distinguish between glasses strong or bad glasses. For GST, for phase change materials, they have poor glass forming ability, and so they are bad glass former, and the stark tendency to relaxation of amorphous space. So please think about this measured resistance is increasing with time. And the phase change alloys also show better relaxation, and this is indication of fast atomic motion in glassy state. And to reduce resistant drift, you should restrain this atomic motion and suppress structural relaxations. So let us move to another part of this lecture. And here I would like to talk about the crystallization kinetic and its tailoring. So from the lecture 1, we know that this crystallization speed, it's an important parameter for phase change device, and it influences the PCM device performance set pulse and also energy consumption. And this crystallization speed, it depends on the crystallization ability of amorphous state, so how fast this amorphous state can be crystallized. So here I will look, in this part of my lecture, I will look to the crystallization kinetic and how to measure it, and also give some numbers of the crystallization kinetics. So, but first let's define some basic properties or some definitions. What is how the materials is crystallizing and grown. So in the crystallization of liquid or amorphous state, we have two processes like crystal nucleation and growth. First, this is crystallization is initiated by crystal nucleation. Here we also distinguish between homogeneous and heterogeneous nucleation. In the homogeneous nucleation, the nucleation occurred in the interior of the parent phase and without the involvement of foreign substance. And the heterogeneous nucleation, this is in the parent phase is in contact with the foreign substrate, and this substrate detects as a nucleation site, like we have seen before in the case of the epitaxial recrystallization of amorphous material. And then the second process in the crystallization, this is the crystal growth. Here, if you have a stable nucleus, then it can grow and in different directions, so to microscopic size. Now let us look to the properties of phase change materials. So they are summarized here on this diagram. There are mainly two groups of phase change materials. They possess either nucleation-dominated recrystallization or growth-dominated recrystallization. One group, these are also called germanium telluride, antimony telluride phase change materials, which are lies on this timeline, like GST. And the growth-dominated recrystallization, these are materials like AST or antimony-rich alloys, like germanium 6 tellurium. And so what is the difference between these two recrystallization processes? One is that here the crystallization kinetic is dominated by nucleation, so you have many nucleus. Here they nucleate, and then they grow a little bit. In the case of growth-dominated crystallization, as soon as you have this nucleus, stable nucleus, then it starts to grow to the large crystal. So this is one example of such growth-dominated crystallization. Here, this is no amorphous phase, and after several 1,000 nanoseconds was laser crystallized. We have a large crystal, and then the crystal started to grow in all directions. And here there is no other nucleations in this material. In the GST case, you have nucleation on different sides, and then after this area fully covered by small crystals. So now, but before to form such a stable nucleus, there is also one parameter like incubation time. So incubation time, this is a minimum time to form a critical nucleus. And in the case of phase change materials, there are, as you know, amorphous state which can be produced by deposition, or you can quench the crystalline material, and then you get another amorphous state. And we saw already that there is structural difference of this state, but there is also a difference in the crystallization kinetic of these both states in the sense of the time of critical nuclear formation. So for age-deposited film, there also some basics for the critical nuclear formation. Of course, this nucleus formation, it's a temperature, it depends on the temperature. So if we increase the temperature, we need less time to form this stable nucleus. In the case of GST, of age-deposited GST225, this incubation time is on the average of 100 nanoseconds. if we use melt quenched amorphous GST225, this incubation time can be decreased, and it can be seen in the crystallization time, which is on the average of 10 nanoseconds. Also for magnetron for germanium telluride, also some values which are which can be related to incubation time. So indirectly, the crystallization time of GT of S deposited is like 1000 nanoseconds, but of melt quenched this is 50 nanoseconds. So you see a huge difference in the crystallization time, and this is because of the shorter incubation time. Also some data on crystallization times of different phase change materials, ranging between GST to IST. So what we can see here, that the antimony-rich materials, they have lower crystallization time compared to the GST-based materials. So, but there is also some spread here, and so the highest crystallization time is always achieved for composition containing antimony and tellurium. Also, there is a compositional dependence of crystallization time in the case of the GST. So here we see the crystallization times of 2 to 5 composition, 1 to 7 and 1 to 4. And so we see that they are different from one composition to another. So there is no value for crystallization, no crystallization time which is typical for phase change material. Even for GST material, this crystallization time can be changed. So in the literature, you find sometimes that this glow-dominated materials, the kinetic of glow-dominated materials, they stated that the crystallization occurs much faster, because if you have crystallites, it can grow very fast, and they may be advantages for using for phase change materials. But in phase change devices, phase change memory materials, the industry, they use still GST 2 to 5 or 1 to 4. Of course, they make a doping to reduce the endurance here, and this can be understood from the recent studies of Matthias Wutig group in 2024. And what they studied the nucleation time of different phase change materials, ranging from the nucleation-dominated to growth-dominated materials. And they also studied the growth time of these materials. And the results are very interesting from my point of view, because first we found that the nucleation time of nucleation-dominated materials are very short. They are shorter compared to the growth-dominated materials, but the growth time, they did not change a lot for all compositions. So the nucleation-dominated materials can be also fast and much faster regarding the crystallization, even faster than this growth-dominated, because you need longer time first to make nucleus and then to allow to grow of these materials. So now how to measure crystallization kinetics of phase change materials. There are different approaches, based on isothermal measurements, or many uses the laser setups. So in the isothermal measurements, we use also laser to see the phase change between amorphous crystalline or in this case you use amorphous crystalline, and here you use thermocouples to measure the temperature, and then you heat up and look with laser what's happening in your specimen. But here this setup is limited by the time scale. This is by linear time scale. Of course you can increase this maybe by fast heating setups. Another also setup, this is direct, based on direct laser heating, and here instead of thermal heating element they use laser heating, and then this is like prompt laser, and then we can measure the crystallization or amorphization times by using CD laser, constant wave laser. Nowadays you can achieve different resolution times. Also you can use different pump laser ranging between nanoseconds to femtosecond. The resolution time can be also on the range of femtosecond scale if you use special setup like a string camera. So here we can achieve like nanosecond time scale to femtosecond time scale. So how this setup is working? Here, if you have a material with low reflectivity, then if you make crystallization pulse, the reflectivity change. You can see it by your detector, and then if you make crystallization, you can also see the changes. Here, this slide shows you maybe more insights how it's working. So here we started epitaxial film field in this setup. So here this is the axis. It shows reflectivity against the time, and if we apply nanosecond pulse here with duration 20 nanoseconds, then what we can see that the reflectivity of our GST materials is changing. So here we see the transformation to the amorphous state, and then after around 20 nanoseconds, we can see the recrystallization process, so transformation from amorphous to crystalline state. So this is very nice and very sensitive technique with time scales of nanoseconds. And here we can see our two phases like cubic and trigonal. By combining these time dissolved measurements with TM measurements, we can measure crystallization speed. Here from this data we extract the amorphization time or crystallization time here, and this is T, and D, this is the thickness of recrystallized area, and by using this D divided by T we can find the recrystallization speed, which is also here. This is the time for recrystallization. So now if you do like this, we can measure it. We can irradiate the thin film or epitaxial thin film in one setup. So we have one thin film having almost same structural properties at different places. The spot size of here of the laser, we can adjust it. It can be on the micrometer scale. So if we can produce here different regions like amorphous to crystalline areas, and we can see nicely even optically. So then we make such studies on the recrystallization process. So again we have here amorphization and then recrystallization of CGST. If we radiate with different laser pulse, we can see transformation to the whole CGST, or also at higher laser energy to the amorphous state. If we then draw the growth velocity against the laser fluency, we can see like exponential dependence. So it's higher fluency, we have some saturation here. But what we can see that at low fluency we have a low recrystallization rate, and at higher fluency we have like recrystallization rates approaching 1.7 meter per second. So why is there is a difference here between two values here, two different fluencies? We can explain it based on the cooling rates. So for low laser fluency we have low cooling rates, for higher we have higher cooling rates. So here we can maybe achieve the cooling rates needed for amorphization process, like 10 to the 9, 10 to the 10 Kelvin per second. And so if you compare this value of 1.7 meter per second, we can find that this is in a nice agreement with other measurements, which are also on the range 1 to 2, and also theoretical calculations. They show also the value on the range of 1.5 meter per second. As you can see, that the crystallization of GST from amorphous space it's not so fast. Even some people can run 100 meter faster than the GST is going. This is for nucleation dominated material. For ground dominated material, this value can be a little bit larger, like in the range of 5-6 meter per second. Now also let us look to the amorphization time. This is also important parameter, and it can be also measured in such laser setup. So in our case, if we use our setup, we measure amorphization time of like 15 to 12 nanoseconds, depending on the cooling rates. In this setup, in optimized setup, here there is a GST layer sandwiched between the aluminum layer and it's glass substrate. This is GST, and this is GST layer, and this is zinc sulfur CO2 layer. So this is optimized stack. This is without additional stack. And what we can see here that the amorphization times here doubles. So if we can adjust cooling rates, we can also adjust the amorphization time, so we can increase this. Also, this value amorphization time was not optimized. It was by us. We did it on silicon, but it's in this range. So a nice agreement between different experiments. Also, some reports they report the amorphization time in this range of even of a femtosecond scale. So what we can learn from this, we can learn that the amorphization time depends on the cooling rates, and so if we know about this, we can adjust the device geometry to get the best performance from the material, phase change material. So now let us look to the how to tailor crystallization of phase change materials. From previous lecture, we know that first that the phase change materials they crystallize fast, but the rates of this crystallization are still low than compared to the DRAM and SRAMs, which operates in a sub-nanosecond time scale. We showed that crystallization or amorphization can be achieved on the nanosecond time scale, but we need to reduce somehow this to the sub-nanosecond time scale. So the issues we know already, they are connected to some intrinsic properties of phase change materials, namely to the stochastic nucleation, and for the formation of nucleus, we need at least 10 to the 5 atoms. And also next issue that this nucleus is stable, so it can form and reform. So we need to stabilize somehow this nucleus. And now the question is how to reduce the stochasticity and stabilize the nucleus. There are different solutions and different strategies found in the literature. One is the programming strategy. Another is materials, again, materials engineering, which is done either by doping or by composites formation, or this interface assisted crystal growth, or by nanoscale engineering like heterostructures and superlattices. So let us look to the first strategy, like pre-programming strategy. This pre-programming strategy is based on the formation of nucleus before the full crystallization of materials. And so how it's achieved in the phase change cell? It's achieved by the pre-programming with low voltage or low current pulse. So you use very low pulse, the low amplitude, and then you induce the induce some pre-ordering in the amorphous phase. The simulations based on this method, on this idea, it shows also that it can crystallize faster. So this is amorphous phase without pre-ordering, and this is the pre-structural ordering. So here we have some nucleus, and then they can accelerate the growth. So also here some AMD simulations on the pre-annealing and crystallization of phase change material. Here it shows that one can obtain the faster crystallization of the material if we make pre-annealing, like if we do some nucleus before the full crystallization of the material. And this is also connected to the local structure of the amorphous phase, that if we look to the distribution of four-fold rings in this pre-structured ordered material, then we see that the distribution of these rings is depends also on the time, and they also influence the total nucleation time. So we know that these AB rings they act as a nucleus. So now let's look to some properties of such pre-structured amorphous phase. So here the authors use different incubation voltage, like 0.1 or 0.2. This is much lower than of the crystallization voltage of the cell. And then here, if we look to the switching speed of such pre-structured materials, we can see here that this is the without pre-structuring, and this is the with structure 0.3 volt If you look to the dependence of the set voltage, we can see that for pre-structural cell we need much more set voltage compared to the non-pre-structural cells. So here it's possible to achieve the crystallization speed on the range of 500 picoseconds. We are now in the range of sub nanoseconds, which is a requirement for DRAM and SRAM. Also stable switching after 10 to the 4 cycles with set voltage of 1.1 volt and reset voltage 6.5. So if you can make pre-ordering of your amorphous phase, you can achieve such nice characteristic of phase change memory cell. Another approach is based on the stabilization of such a AP ring by introduction of doping elements. In this case, if the scandium is introduced to the antimony telluride, then the number of such AP rings which correspond to the nucleus, it also increases. So this is for scandium. This is SST, our scandium doped antimony telluride, and this is GST. And if you look the fraction of this AP ring, you can see that for scandium doped material, it's a fraction of much larger compared to the GST. And this doping also brings introduce one effect, that it brings the stabilization of this nucleus at different temperature. So again, for GST, these AP rings can be formed, then can be reformed, can be also destroyed. So these such nucleus are very unstable. And in the case of scandium doped antimony telluride, these rings they stay very stable at different times at this temperature. This is the IMD simulation. So again, this can also bring to the shorter incubation time and to the faster switching speed. It was also shown in the experiment. So in the switching of the real PCM cell based on this SST material. So here you see the set speed independence on the set voltage for SST, and this is for GST. What we can see that set speed is at different set voltages is much lower than of typical GST material. So you can achieve the set times which are even less than one nanosecond. So again, we are going here to the sub-nanosecond range. Also, you can achieve very stable switching between set and reset states, and also cycling endurance is also very high, very nice for the application with very short pulse length. So now let us look also to some another doping like scandium can make this possible, this fast switching. Titanium is also introduces also the same effect, so it's induces also much stable, the formation of much stable AP rings, and correspondingly it's possible to achieve faster switching times. So these are some experimental data on the set speed independence of voltage for GST, and this is for TST. Again, we see the that the set speed of TST is much faster compared to the GST, but the speed time can be improved, but we cannot reach like the values as for Scandium, so it's on the range of 6 nanoseconds. It's much faster than GST, which is on the range of 75 nanoseconds, made all the same technology, CMOS technology, but the doping with titanium, it can reduce the reset current to 82%. So this also leads to the reduction of energy consumption in such cells. So now let us look to the compounds. In the case of compounds, you can create a composite material consisting of, let's say, phase change material and another material like silicon dioxide. And the idea is here, we know already from previous consideration that we make here heterogeneous nucleation, so the phase change material can nucleate from the interface between amorphous silicon dioxide and can grow faster as without this additional material. Here, again, the idea that to increase the number of nucleation sites for your material. And here again, there are some characteristics, switching characteristic for this composite that's shown here. So the set speed and set voltage. We can see that the composite is operating much faster compared to the GST. So here we can reach the values still not under the sub-nanosecond scale, but these composites are much faster, operate much faster. So from this we can learn that the interfaces can play a role to enhance crystallization rate of phase change materials. And here we can also look, I showed you already how the interfaces play a role on epitaxial crystallization of GST material. So this is we showed already in the case of TM that if we have a crystalline interface, we can increase the number of sites and such crystallization from the interface, which is much faster compared to the homogeneous nucleation without such nucleation sites. So I think this example I considered already, and we know that the crystallization here in this case we can achieve up to 1.7 nanometers using this interface assisted crystallization. And the crystallization time, this is on the range of nanoseconds, 50 nanoseconds, and it also depends on the energy used for the crystallization process. This slide can be go until 0.5 nanoseconds. They use also superlattices. This is in the topic of nanoscale engineering. Here, if you produce the superlattice structure consisting of germanium telluride, antimony telluride layers, and if you integrate it into the PCM structure, PCM device, then you can also get the much faster set pulses, like in the range of 5 nanoseconds, and using the same setup, the authors, they achieved crystallization time in the range of 10 nanoseconds. So you see here the crystallization time is increasing, is reducing by 2 times. This was the first publication in this direction on the superlattices. Of course, they were then much improved, and also they achieved low reset time, and this superlattices are based on amorphous crystalline layers, and if you use the crystalline superlattices like textured or epitaxial thin films, then they can also get better performance in the sense of endurance, low currents, but crystallization times is lower than of GST225, but still on a nanosecond time scale and not on sub-nanosecond. But here we can reduce the energy consumption. Also, we can reduce the endurance here, cycling endurance here. And it was one of the first work. Then there was improvements in this direction, and we will see in the next lectures how on the improvements of this phase change in superlattices. We have an extra lecture on this on heterostructured materials, and I will be talking about tomorrow. So for today, that's all. We have some time for discussion. If you have any questions, please ask me.
Yeah, so the session is open for questions. So if anybody is having any query, so you can ask the speaker.
So sir, this is regarding the pre-program strategy. So would not the pre-program pulse, hence the pre-program ordering reduce the amorphous stage resistance, hence the resistance contrast?
Yeah, but it reduces not for, it's still enough. Here we use one big cell. So here this is not a big deal to reduce little bit the resistance of the cell. Because the cell it still stays in amorphous state with little bit lower resistance as deposited. But it's still enough. The resistance contrast, as you know, is 2 times order of magnitude. This is large window, GST has very large window. So it's enough to read the information. Okay, of course, you should select very carefully this incubation voltage. Should not go to more than this. Yeah, please.
So Professor, in slide 24 you were discussing about amorphization time that depends on the cooling rates and also on device geometry. Yeah, so wanted to know that I think in slide 22 or 23 there is something, this one. So 22, correct. So we see that the recrystallization time which sticks like in 40 nanosecond time scale. So is there any way that we can ramp it up faster by changing the laser pulse duration or something?
Yes, I think it's possible. First, we can maybe reduce the size of our GST film, or also can reduce the efficiency of our laser setup. But then the problem would be that it can damage our material. This is a problem.
So there is a limit to the ramp up time, right? We could ramp up it as fast as possible.
Yes. Yeah, but it's covered mainly by the underneath substrate. So first by the surface, they have cooling starting from the surface, and also cooling is also given by the substrate itself. Silicon that has high thermal conductivity, so can nicely dissipate the thermal energy, heat down, and yeah, if you maybe can optimize also the system and nanoscale it here can make the cooling rates much higher. You can get much higher cooling rates, or then also achieve much higher crystallization rates. Depends on the purpose.
And also, I was not clear about one thing. Like at some point in slide 20, you talked about nucleation dominated materials has faster crystallization rate than growth dominated materials. So can you just reiterate? Like I didn't actually catch that part.
So again here you can see that if you consider the nucleation dominated materials, so the crystallization kinetic is governed by the nucleation. So if you want to crystallize the bit, you need many nucleus to get the crystalline, fully crystalline bit. So, and for the formation of nucleus, you need some energy. You need to overcome the energy barrier to form the nucleus. So it's believed this formation of nucleus is the main step in the crystallization process. And it's very time and energy consuming. In the case of the nucleation dominated material, as soon as you have this nucleus, the crystal is growing, so it's very fast. So here you need maybe a little bit longer time for the formation of nucleus, but the growth is very fast. So and here was believed that this material is much faster. As the whole, if you want to make like a bit here, crystalline bit, it forms faster as in the case of the nucleation dominated material. But here in the case of GST, it was shown that the nucleation is here much faster as the growth of the growth dominated materials, or on the same range. So it's the total crystallization kinetic is same. So there was many discussion. If you read papers, you can find that such materials are faster, and that is why we need to develop these materials. But now from 2024, you know, this is not true. So they both are very fast.
All right. Thank you.
Yeah, please.
Any more questions? Okay, so just I wanted to know, you discussed about this incubation voltage assisted switching. Yeah. So during selection of material for such kind of application, I mean, this effect, it is more on nucleation dependent material or growth dependent material. I mean, this process, it is specifically for this, or both type of material showing this fast and low power switching in incubation assisted? Yeah.
I think it's from the common knowledge. First, we need to form a nucleus, stable nucleus, and then if we have this, then we can crystallize the bit. So I think it should be look nice for both. For nucleation and growth of dominated materials, but because GST is of interest for industry, it was done for GST, because it's more stable.
So actually, during this incubation voltage, so the material is getting crystallized, or it is still in the amorphous phase, and just we are providing some kind of power. I mean, but in material aspect, how we will understand this process?
Yeah, just if you look to the RT curve, if you can remember this, yes, resistant temperature, and we have here like several transitions. So this is from amorphous, and then we have here crystalline and the head crystalline. And here this range is fully amorphous, so we can have different structures here. And this is the idea, to make the pulse more moderate here. And because this resistance is a little bit lower, as you mentioned, but it's still amorphous. But the structure is different, a little bit different, as here, as for this. And this is the main idea of this pre-programming strategy. Just doing this little bit more moderate phase. And this is also the main problem with GST, that this nucleus, they are unstable. You can form, but maybe it can be again relaxed. But for if you want to operate the cell, you make this, then operate, and again make this.
So, any questions? So now we are almost going to end our first half session of Dr. Entry. So then after that we can have after break we have tutorial session on this magnetron sputtering system, and then this 4-probe resistivity measurement setup. So that will be taken by me. So I will explain here about this how we can do this 4-probe method, and about this experimental setup we can go to the laboratory and we can see the setup and all. So we will cover accordingly. Okay. So if there is no more questions, so then we'll wind up the session here and we'll meet after break. Okay. Thank you.